All right, going to start with this right here. Two main types of electricity transfer. Yeah. All right. So the way we do this is show you guys a little bit about circuits, and I'm going to back up to electrostatic force, and then we'll go back to circuits in the class today. So two main types of currents. There's a direct current and alternating current. So direct current is anything that you hook a battery up to. So if you have a watch or a smartphone or have these clocks on the walls, right? Anything has a battery plug, your calculators got batteries in them, where there's an actual net movement of electrons, say from the anode of a battery to the cathode, right? Because electrons go from negative side to positive side. Now, if you look really close, you see, do you guys see these red dots are actually going from the positive lead to the negative lead? Right? Isn't that actually backwards of what electrons do? Right? By the way, the speed of the electrons in the calculator was extremely slow, something like it's like order of magnitude like a millimeter per second, so something crazy slow. But the energy that pulses through goes like extremely fast. So it's closer to the speed of light. Right? But why are these red dots going from the positive to the negative? Why is that? It has to do kind of a quirk of history. When people were first laying down the rules of electricity, like back in Ben Franklin's era, so like hundreds of years ago. They knew there was like some kind of charge flowing, and they did a coin flip as to what the sign of that charge was, and they picked the flow of positive charge. Right? And then, a couple centuries later, people discovered the structure of the atom and realized, no, actually, it's the motion of electrons, which are the negative charge. So, oops, they got it backwards. It was 50-50. But it's just one of those conventions that's stuck in the textbooks like down through the eras. But mathematically, it makes no difference because of symmetry. So whether you define current as flow of positive charge or negative charge, mathematically works out the same either way. It's sort of a technical thing that once you just know that, just okay, whatever, right? But look at the picture on the right. See all those electrons? There's no net movement and alternating current. They just kind of slosh back and forth. Okay. Now you can still transfer energy, right? Kind of like waves propagate. You guys remember breakout slinky? You can like propagate waves along the slinky, and there's no net movement of any metal part of the slinky, but there's an energy pulse, right? That's kind of like alternating current. Now, alternating current is particularly useful for electric grids, like sending electricity across a whole grid system, because it's very easy to step up and step down the voltages with the transformer that Butch showed you guys too. And see, otherwise, like if you try to create a direct current like power grid, it would just not be very efficient. You would lose a lot of energy that way. With alternating current, you pump up the voltage with the transformer to like thousands of volts, and then you can set it down when it reaches, say, like a school or a house to about how many volts? If I plug something into one of these outlets here, how many volts is that? 120. Good call. 120. And depends where you are in the world. So if you go over to Europe, they're like double the voltage. I bet a lot of you guys know like a lot of stuff I'm going to tell you guys today. So they're on like a 240 volt standard. And before I show you this next graphic, quick history. Let's go back to the 1890s again. 1890s. I bet a lot of you guys know something called the War of the Currents. The War of the Currents. Okay. When some of the very first appliances were being developed for household use, like some of the first electric lights, again, back in the 1890s, people were trying to figure out what standards are we going to come up with to create our grid systems, and which of these should we actually use? Should we use DC or AC? Which scientist is associated with direct current? Yeah, Edison, Thomas Edison. And probably because he owned a lot of the patents associated with that technology, right? And which scientist was associated with alternating current? Yeah, Tesla. So Tesla was designing the generators that would have this alternating current. Okay? And of course, that it was maybe like almost inevitable, probably that alternating current would win out because it's just a better system for grids anyway. But so not only do you have to come up with a common voltage standard, which in the States we're all using about 120 volts. But also, do you guys think there's some frequency associated with that back and forth motion that also has to be standardized across the grid? And how many hertz alternating current here, say, in these outlets? Is it being 60 hertz? We're on a 60 hertz standard. So here's the different standards around the world. So all North America is approximately 120 volts, but you get a little bit of a window, a little bit of leeway. But the frequency you have to get like exactly on, right, to make appliances work. The other main standard, of course, is like double the voltage in a 50 hertz. So all of Europe, for example, is on a 50 hertz standard. Right? So yeah, if you ever vacation in a different country, make sure you have like some kind of adapter, or you can't just like plug in your appliances because there's like too much voltage and like the wrong current. Now, cell phone adapters or a lot of laptops will also have some adapter where it will take in any of these scenarios and then turn into direct current so that your devices will run. Okay. Oh, something else I want to look at here. This light bulb. So, see the shot of this light bulb. Now this is in slow motion. Do you guys see it pulsing? Right. Now that is not in real time. This is in slow motion. But if you did speed this up to real time, you guys want to take a guess how many pulses per second that is? 60 is a good guess. Tell you what though, you remember back when we were setting standing waves on a string, and that if there were like 2 loops that corresponded to like 1 wavelength, right? Very similar thing here. So if it's 60 hertz, right, times 2 gives you, yeah, about 120 pulses per second, right? Or if this is over in Britain, then it might be like 100 pulses per second because they're on a 50 hertz standard or something like that. All right, so there you go. Switch back over here.